Howdy, howdy, howdy. So today I want to talk about combining like terms, and in particular relating it to the properties we know about real numbers. First of all, I do need to clarify that when we are talking about combining like terms, we're talking about algebraic expressions where the variables represent real numbers. Technically, everything we talk about today would work for things like complex numbers as well, but the focus will be on real numbers. So let's start off, first of all, by reminding ourselves about a few properties of real numbers. Okay, so the first properties we'll talk about are the commutative properties. With the commutative property of addition, what this means is if you change the order in which the add-ins are written in a sum, it does not affect the actual sum value. So the way you write this is we can extend this to a commutative property of addition, not just for real numbers, but for algebraic expressions where the variables are representing real numbers. We can simply rewrite this as for any algebraic expressions where the expressions are a and b, where the variables take real number values. We again get a plus b equals b plus a. Side note, this notation here is something that you'll actually see a lot of teachers use in case you haven't seen it before. These are basically little quotation marks. Each one just means repeat what's above it. Okay, so if you see these two marks, that just means repeat what's above it. So this says for any algebraic expressions a and b, etc. Let's look at next the second commutative property, and that's the commutative property of multiplication. Now for this one, I'm actually going to skip over this first part. I'm not going to bother writing it just for real numbers because real numbers count as algebraic expressions. If I have, 5, that's an algebraic expression. So is 5x or 5xy or 5xyz squared w. Okay, that's an algebraic expression. I can add stuff. Okay, those are all algebraic expressions. So I'm just going to write the algebraic expression version. So in this case, it's the commutative property of multiplication, so we get the same thing as before. You can change the order, but instead of addition, the property is multiplication. Okay, I do want to make a note of the fact that adding these together or multiplying these together might involve other operations, because these expressions could have all sorts of stuff inside of them. So just keep that in mind. One other note about abbreviations, notice over here and here, I did use an abbreviation for the word number. It's a pretty common abbreviation, but there are some people that might not be aware of that, so it doesn't hurt to talk about it. Okay, next up, the associative properties. Once again, I'm going to skip the version that's just for real numbers and we'll just focus on algebraic expressions. This time we're going to need 3 of them. for any algebraic expressions, a, b, and c this time, where again the variables take real number values. Now we're talking about adding those three. And so if you were to follow the order of operations as generally given, they say go left to right. So if I wanted to add a plus b plus c, you would start by adding a plus b and then add c. But it turns out that the order doesn't actually, not the order, sorry, the grouping of these add-ins doesn't matter. So you could instead add a to the sum of b plus c. Next up, our second associative property, but this time it's of multiplication. Okay, now because I'm on a computer, I'm going to go ahead and make my life a little easier. And I'm going to note that I'm once again going to need the same introduction. Okay. So the only thing that changes is instead of addition, we're looking at multiplication. So we have the product of a and b times c equals the same thing as if we had multiplied a by the product of b and c. So those are the four properties that deal with one operation each. There's a third property that we care about quite a bit that is called the distributive property. If you take the product of a times the sum of b and c, that's the same thing as the sum of the products ab plus ac. Okay, each of these things can be justified by looking at the properties in detail in terms of what they fundamentally represent. That's a whole other subject itself. Instead, what we're going to focus on is the applications of them. So let's start off by looking at an example. So let's say we want to simplify this expression. Okay. Now, often when people introduce combining like terms, they spend a lot of time talking about what like terms are. And we will talk about that, but I want to emphasize how it works first before we talk about that. Because otherwise it just seems like an arbitrary thing. Like, okay, people defined like terms this way, so what? So let's look at this particular example. So we have 4x squared y and 7x squared y. So what I'm going to point out here is that we have this expression that's in common in both of these terms. Okay, that's like these here. So technically, if we wanted to use the distributive property as written, we want those written first. And so this is an example of where technically we are using the associative property of multiplication and the commutative property of multiplication. Because what's actually happening is we're going to say, instead of moving left to right, 4 times x squared, and then times y, and then 7 times x squared, and then times y, we're going to first regroup them so that the x squared y part is its own expression. Then we'll use the commutative property of multiplication to write them first. Now it's really set up nicely for using the distributive property as we wrote it before. So here we have that a that's in common, except now the expression that a is representing is x squared y. So the distributive property tells us we can instead treat this as a, which in this case is x squared y, multiplied by the sum of the two other values. Well, what are the two other values? Well, b is whatever we've multiplied by this first one. And then c is whatever we've multiplied by this second one. Okay, so that means now we have an expression where we have inside this set of parentheses over here are simply two real numbers that are not variables, they are constants that we're supposed to add together, so we can go ahead and add them. And then finally, because we tend to like writing the coefficient first, we can use the commutative property of multiplication to write the 11 first. And I'm going to not write the 11 in parentheses anymore, they're unnecessary. And then use the associative property to write this without the parentheses. Okay, so that's an example, but let's look at the distributive property in the general case so that we don't have to do this business we started out with here, where we had to switch the orders and whatnot. For any algebraic expressions, still going to be A, B, and C, where again the variables in these expressions take only real number values. We can either write it as the way we had it before, or actually I should say and we could also rewrite it in the reverse order. Okay, and if you wanted to go through a proof of this, which I encourage you to try out, you would essentially take, copy down this same idea here. It's just instead of 4x squared y and 7x squared y, you would have BA plus CA. But then you switch the orders so that the A's come first, and then you use the original distributive property to essentially factor out that A. And then you would use the commutative property again and be finished. So I encourage you to try to do that. Now that we have that, let's talk about what it means to combine like terms in general. So if we wanted to be able to do this type of thing that we did in our example up here with some other situation, we need it to have something in common with our previous example. And basically, there's two things that were important in here. First of all, we had the fact that there was this common factor. The second is that there was addition here. Now, technically, it's okay if there's subtraction here instead, because subtraction is equivalent to adding a negative. That's going to be our general form. We have something times an expression plus something times that same expression. And then we can combine those two terms into one. Okay, so two terms that have the same, what we call here, this is called a literal part because it involves letters, okay? If they have the same literal part, then you'll be able to use the distributive property and combine those like terms. So a like term, a pair or more of like terms is just two or more terms that have the same variable part. Okay, so let's look at a general example. We're first going to start off with two real numbers that are going to be our coefficients. So since they're coefficients, I'm going to call the first one K. I know you thought I was going to say C, but we've already used C today. So K, which is like C, and C is for coefficient. And then we're going to have a second letter, which I'll just use L because it's right after K in the alphabet. Okay, so we have two coefficients. In particular, they are real numbers. And just to emphasize the fact that they are coefficients and not part of the variables, we'll emphasize that they're constants. Okay, and then we'll have some literal part. Now, a lot of times people just say, okay, use x. But the problem is that x is typically thought of as simply a single variable. And I do want to emphasize that we're talking about any literal part at all. So what I'm going to do is I'm again going to use A as an algebraic expression. Okay, now typically if you're going to be combining like terms, you want it to be an algebraic expression that's, say, a product of variables or a single variable, but it can be other things. And when dealing with situations like factoring by grouping, you are sometimes going to look at situations where this second part of each term is more than just a product of variables. Okay, let's finish this off. So then we can combine the like terms, and I'm going to put this in quotation marks because technically they're only considered like terms if A is, like I said, something like either just x or x squared, or maybe x squared y like we had in the example. It wouldn't include things like x plus y. Usually those are not considered like terms in that case. So we can combine like terms. Ka plus La by applying the distributive property. And particular distributive property up above. Okay, so let's see what this looks like. Okay, so we have Ka plus La. Using this form right here, we have this situation. Okay, it's just instead of B and C, we have those constants, K and L. So then what I can do is I can factor out the A by writing K plus L first. And then we multiply that sum by A. Okay, so that's the general form. Let's look at an example. So this time, let's add 9 WZ cubed. This time let's use a minus sign. So minus 14 WZ cubed. First of all, again, in order to provide an example that makes sense for this, they do have to have that same algebraic expression in both of them. So that's the A here is WZ cubed. So that means we're going to take 9 WZ cubed minus 14 WZ cubed. And so technically, before we try to use this combining like terms statement up here, we need to first write it so that it's an addition problem. Okay, now that we've done that, we can simply rewrite this as the sum of the two coefficients. So we had 9 and negative 14 times that common expression A. Okay, here's our common expression A. So then we have WZ cubed. This means we can now go ahead and add 9 and negative 14, which is going to be negative 5. And then we're left with our WZ cubed. And that's it. Now, we can apply this to a lot of different situations. Let's do one more example. And we'll use more properties than just the distributive property used to combine like terms. Okay, so first of all, let's use some fractions in here. It's been a while since we've used some fractions. So let's use x plus y, and then minus, let's make this one an integer. Okay, and then let's also add, let's say 1/6 x minus 3/2 y minus 8xy. Okay, so notice that this is much more complicated than the previous two examples, but it's all going to use the same stuff we've been talking about. So we're just going to look at it one piece at a time. So the first thing I'm going to do is note that the associative property is what allows us to write this without parentheses. So simply by writing this without parentheses, I've already used the associative property of addition. Okay. Similarly, the fact that these terms here, the 6xy and the negative 8xy, since those don't have parentheses in them, again, I've already used the associative property of multiplication. So I'm not going to write those out separately as applying them because I've already applied them. But what I am going to do is I'm going to use the commutative property of addition to move things around. Also, I'm going to make a note of the fact that I am going to think of this as a plus negative 6xy, a plus negative 3/2 y, and a plus negative 8xy. So just to keep things from looking too messy, I'm going to delete those annotations, but you'll see them pop up, see those same things pop up when I reorder them. So what I'm going to do is I'll start with the x's, just because that's first over here. So I'm going to write 2/3 x, and then plus 1/6 x. So I've now taken care of these two terms. Okay, I've added them together because of this plus here. And then I'm going to use the commutative property. Again, technically we're using both the commutative property and the associative property because I'm not writing a bunch of parentheses in here for groupings. So next up, I'm going to have my plus 3/4 y. So I'm just grabbing this one right here. Okay. And then I'm going to add negative 3/2 y. So that's what I was talking about before, where I'm going to treat it as plus negative 3/2 y and use the commutative property of addition. And so let's keep going. So next up we have our negative 6xy here, which again I'm going to treat as plus negative 6xy as opposed to minus 6xy. And then I have another minus, so plus negative 8xy. Okay, so in order to combine these like terms, I'm going to end up adding some fractions. Okay, I have 2/3 that I'm going to have to add to 1/6. So in this case, this is where we have the situation where K is 2/3, L is 1/6. Okay, K and L, K and L. Okay. And then we do the same thing here. We have 3/4 as our first coefficient, and then negative 3/2 is our second coefficient. And so the sum of those is then multiplied by y this time. And then finally we have a negative 6 and a negative 8 times xy. So in order to add these fractions, so then I'm going to multiply this by 2/2. Okay. What I'm going to do is I'm going to keep dealing with this one here, just because I've already got my brain thinking about that. You don't have to do it that way. If you want to deal with the entire row here, that's fine too. Okay, 2 times 2 is 4, 3 times 2 is 6. That's the reason I multiplied by 2/2. I can multiply by 2/2 because 2/2 equals 1. Okay, and then finally we have 4/6 plus 1/6 is 5/6. And then we'll have the rest of it in a moment. But let's go back and fill out more information in here. So again, we had 3/4 plus -3/2, but this time I'm going to multiply by, once again, 2/2. And that's so that I get that common denominator of 4. And I'm going to go ahead and change this to, instead of plus a negative, I'm going to just subtract this. 3 times 2 is 6, and 2 times 2 is 4. So 3/4 minus 6/4 is -3/4. Okay, finally, this one is nice. I'm just going to first write it as -6 minus 8. If you want to think of it still as -6 plus -8, that's fine too. In any case, what are we going to get? We're going to get -14. Okay, and so that's unchanged because it didn't take as many steps to simplify. So finally, I'm just going to rewrite this without the parentheses and simplify those plus minuses into just minus. Right? Technically, I should say plus negatives change to minus. I hope you found this useful, and have a lovely day.